All right, our next lesson then is looking at 7.5. This is where we're going to come back to that other triangle congruency theorem that said we needed more information before we could use it. Before we totally get into that, let's recall our other congruency statements that we can use. So there are 4 that we've really been practicing a lot so far this chapter. So we have side, 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 angle, side, angle, side, angle, side. Then we can call this one angle, angle, side, or side, angle, angle is also okay if we flip those up. It says recall if 2 triangles are congruent, what do we know about their corresponding parts? So this is the other theorem we've been using a lot in our proofs. So again, if we're talking about congruent figures and their corresponding parts, we know that they are also congruent. And we know that by CPCF, which we've been using in some of our proofs lately as well. All right, today we really only focus on one more theorem, and it has its own section because it is very specific on what you need. So this here is our side-side angle theorem. We did introduce this a little bit in 7.2 and 7.3, but this is where we really get into the specifics of it. So notice, this is kind of why we write it out this way. This is all capitalized, which means this has to be the largest side. And it has to be opposite the angle that's given. Okay, so that's written out in words below. It says in 2 triangles, if SSA is congruent to another triangle with SSA, and the side opposite the angle is the larger of the 2 sides, then we know the triangles are going to be congruent. So here I'm just going to draw some examples. Okay, again, not drawn to scale, as we've probably noticed in this chapter. What this is saying, though, is that if I know the side length is 9, we have another side length of 5 somewhere, we're saying that the angle that's given has to be opposite the longest side information. So this has to be the angle that's given, and this has to be the angle that we know is congruent. That's when we can now use side-side angle or side-side angle. Okay. Here's just when does side-side angle not work? Well, if we take a look at this one here, we drew pictures like this earlier in the chapter as well. But this 8, this length of 8, that could come here like it's originally doing, or as it swings open, this could also be a length of 8 out here. So that's why it's important that the angle has to be opposite the longest side. If we knew this angle was already across from 12, maybe 12 was over here, that's when it would work. So when it's opposite a smaller side than what's given is when it does not work. So let's just practice looking at some information given to see if we can use side-side angle. Okay, so if I look at number 1, the first thing you should notice is that there are no measurements given in number 1. So if there is no lengths of sides and no angle measure, nothing like that, then we can't use side-side angle. So I'm going to say no, not given, side lengths. Number 2, we do have information given, so now we have to see if it's the correct information. So I'm going to come over here, I find the angle that's given, and in order to use it, this has to be the longest side. Well, if we take a look at the information that's given, we know this side length is 20. This is only 16, so this would be a no again. On 3, we find the angle that's given. We look opposite. That is 12.4, so then we would say yes, we could use side-side angle. Over here on number 4, find the angle that's given. We look opposite. Is that the longest side? It is not. 8 is over here. So we would say no. not longest side, opposite. The angle that's given. 5 right away, we can shut that one down. There are no measurements given. And 6. 6, before we shut it down, we do actually have a measurement given. This right here is telling us that this is a 90-degree angle, which means that that is a right triangle, which means this has to be our hypotenuse, opposite. And we know the hypotenuse is always the longest side of a right triangle. So just by knowing this is a right triangle and this has a congruency marking, we can say yes for this one. Okay. We know that the side opposite the angle given is going to be the longest side. So this one has a specific name for it. It's a very specific special case when we use right triangles, and it's called the HL theorem. The HL theorem stands for hypotenuse leg. So you have to be given the hypotenuse and the leg. So we have to know that where the 90-degree angle is as well. So in more words, it says in right triangles, if the hypotenuse and leg in one triangle are congruent to the hypotenuse and leg of another triangle, then the triangles are going to be congruent. So I just draw, this is a special case of side-side angle. If I draw that out, I'm just going to draw 2 right triangles. Right, so I'm going to put my 90-degree markers in. We need to know a leg of the triangle is congruent, and then we need to know that the hypotenuse are going to be congruent. Let's try some examples. So now we're using kind of all of the theorems that we've talked about. So as we look through it, we're going to decide if it's congruent. We're going to write the triangle congruency statement, and then say what theorem lets us say they're congruent. So let's look at the information given for number 1. So number 1, I have a side, angle, side. Same thing over here, I have side, angle, side. That is one of ours, so we'd say yes. I'm going to call this triangle ABC. Triangle ABC is going to be congruent to triangle XYZ, around this way. And then we said this was by side, angle, side. Okay, so make sure you're still following the correct order of writing out the congruency statements. Number 2, let's take a look. So I have a side over here, good. I have angles in between, but then this one goes to a side. This one has a side way over here, okay? So this one was side, angle, side. That does not match because the angle over here is not included. It's not an included angle. So this here is that they are not congruent, and these do not apply. Take a look at 3. 3, we want to pick out that these are right triangles, and we have the hypotenuse across from the right triangles, so we would say yes. Right? We know these are congruent by what we just talked about with the HL theorem. And so I can say that triangle BCA, if I call it triangle BCA to follow the correct order, it'd be PRQ for the second triangle. On the next 3 examples, number 4, now we're looking at overlapping triangles again. We could draw these out like we did in a 7-4 note, so you could kind of look at maybe highlighting or outlining at least one of them if that helps for us to see. So here we have a side, we have an angle, and then we have this angle down here as well. And it's the same thing on this triangle. I have a side, I have an angle down here, and I have another angle up here. So we can say yes to this one. We could say triangle BAC. If I follow the correct order, that would be congruent to triangle CDB. And this would be by side, angle, angle, or angle, angle, side. Doesn't matter how we write it. Either way is fine. Take a look at 5. 5 5, I have an angle, an included side, and an angle. I come over here, I start with the same thing, angle, included side, and angle. So we can say yes. We can say that triangle ABC is congruent to triangle XYZ, and that is by angle, side, angle. Okay, number 6. I come over here, I have a side, side, and we know that this has to be congruent to itself by the reflexive property. So now I have side, side, side for both of these. So we would say yes. I can say triangle ADT is congruent to triangle EDT by side, side, side. Okay, so a little review of all of the different types of congruency statements that we have to use now. All right, couple more examples, 2 examples, 2 proofs, so then you're going to kind of be able to include HL theorem into our options. So on this one here, I think it's number 7 on your sheet, but it says a high fence is perpendicular to the ground. Jack leans a 12-foot ladder against the fence. On the other side of the fence, Jill also leans a 12-foot ladder against the fence, reaching the same height as the first ladder. Why is it no surprise that the 2 ladders touch the ground at the same distance from the fence? So if we take a look at what it's talking about, right? Jack's on one side of this fence. He creates a very specific type of triangle, a right triangle. And Jill's on the other side of the fence. She also creates a very specific right triangle. If we know this is 90 degrees, we know these are the hypotenuse, which tells us that the triangles are going to be congruent by the HL theorem. And so if the triangles they make are congruent by the HL theorem, then the distance from fence to the ladder is also going to be congruent. And that's by congruent parts of congruent figures. Okay, so since they both created right triangles, we can say that the triangles they created are congruent, which means just this distance down here, it's talking about this distance down here on each of their triangles is also going to be congruent. Our next one, it says in ABCD, if we know that angle BAC is congruent to angle DCA, what other facts would we have to be known to prove that the triangles are going to be congruent by side, side, angle? Okay, so specifically telling us to look at this through the lens of side, side, angle. We already know these 2 angles are congruent, so you have to look opposite the given angles. Okay, we would need to know that segment AD and segment BC are longest sides of each triangle. Okay, so in order to use side, side, angle, we have to look opposite the angle that's given. Use that to help us. Okay, let's look at some proofs. 2 proofs for the HL theorem. So if we take a look, you'll kind of have a clue of when to use the HL theorem if we can see there's a 90-degree angle, or if it ever uses, I'm going to add that up here, you might want to add that, or if it uses that things are perpendicular. Just a reminder, some vocab there. Perpendicular means it creates a 90-degree angle. So that is going to be sometimes when we're going to use the HL theorem as well. So let's take a look. We all know we start with our given. So we're going to start with PQ has to be congruent to RS. That is our given. We also are given that it's 90 degree because that's marked in the diagram. So you can use what's marked in the diagram. So now if I mark that up here, if I actually put my congruency marking on here, we know PQ is congruent to RS. As you look at it, you should kind of think about too, what do these two triangles share? And they share segment PR. So we can say that PR is congruent to itself. That is by the reflexive property. Once we have the reflexive property, we do then have the side opposite the angle given is our hypotenuse. So now I can say that the triangles are congruent. You can say triangle PQR is congruent to triangle RSP. We can use our new HL theorem. Because it's 90 degrees, we want to use HL, not side-side angle. And then our last step here is we can say that these angles are congruent. So angle QRP has to be congruent to angle SRP by CPCF, congruent parts of congruent figures. Let's try one more. All right, here we have that segment AD is a perpendicular bisector. So perpendicular bisector means a couple of things for us. The first thing it means, if it's a perpendicular bisector, is that it creates 90-degree angles. But then it also means if it's a bisector, we can also say that these two segments are congruent to one another. Okay. The other given up here is that AC is congruent to AB. So I'm going to go ahead and mark those as well. All right, let's back up and get going on our proof. So first, AD is perpendicular bisector of CB. We also know that AC is congruent to AB. All of that is our given. So we have a couple things that we can talk about here. So the first thing that I might need to define is that I did mark that this was congruent. So CD is congruent to BD. That's where I'm going to go with this one next. So I know CD is going to be congruent to DB, as by the definition of a segment bisector. This doesn't talk about angles at all, right? This is talking about a segment that it bisects. So that's a segment bisector. And then you have a couple options here. You could, for step 3, I'm going to put a little star with it. For step 3, we could say we know that these are 90-degree angles. Okay, so you could say that the measure of angle ADC has to equal the measure of ADB, which has to equal 90 degrees. And we could say that's by the definition of perpendicular, because we know it's a perpendicular bisector. From there, we would follow to using our HL theorem, because now we know they're right triangles. And so now we could say that triangle DAC is congruent to triangle DAB. And we could use today's HL theorem for that, because we know they're right triangles and we had the hypotenuse. Or at this step right here, step 3, we could have gone a different route. If we don't talk about the angles at all, we could have also drawn the conclusion that AD is congruent to itself. And then for our justification, we would say by the reflexive property. And then our last step would be that the triangles are congruent. But now we would say it's by side, side, side. Okay, so you have options there. You could go either route with this one, being that it was in our HL theorem section, probably prefer the HL theorem for this one, but it wouldn't be wrong to go with side by side.